Hello everybody, it's Mr. Ray here again with our next lesson in grade 11 University Math. We are currently working in the trigonometry unit. We reviewed some of the basic trigonometry from grade 10 in our previous lesson, and this lesson and the next lesson they kind of go together. So this lesson is almost like a preliminary lesson to learn some concepts and terminology that are going to be necessary for the lesson, the next lesson, which is the unit circle. The unit circle is something we'll be using as a primary tool for trigonometry for the majority of the rest of the unit. It's very important. Once you know how to use it and once you understand it, it's very easy to use. So what we will do today is learn some of the concepts necessary for that lesson, lesson 3. This lesson's entitled Special Angles. So the first thing we're going to talk about are two special triangles that we'll be using pretty much exclusively in lesson 3 coming up. So we have two of these, and we kind of named these triangles based on the three angles inside the triangle. So the first triangle is called the 30, 60, 90 triangle. So obviously there's a 90-degree angle in one of the corners, and we have a 30-degree and 60 degrees in the other two angles in the other two corners. So I'm going to do a little exercise here using some of our basic trigonometry skills, SOHCAHTOA, which we looked at last lesson. So we're given this triangle, and we've designated the short side here, which you can tell just by inspection. We're going to give that a length of 1. So the idea here is, what are the missing side lengths? So what's this side length and this side length based on this side length being a 1? So we're going to use SOHCAHTOA. So if I focus in on this as my reference angle, and I want to use the sine ratio, okay, so I'm going to just write something to start off with. So if I was looking at sine 30, so there's my reference angle. So sine 30, remember, is opposite over hypotenuse. So what's the opposite side? Well, the opposite side is 1. And the hypotenuse is over here. We don't know what it is. So for now, let's just call it A. And put an A here. Okay, so how do we figure out what A is? Well, if we want to solve for A, there's a couple ways you could do this. What I would do as one of the ways is multiply both sides with A. So I get A sine 30 equals 1. And then divide both sides by sine 30. So I get A equals 1 over sine 30. Hopefully that makes sense. The other thing I could do also, which is actually more direct, is if I thought of sine 30 as a fraction, sine 30 over 1 equals 1 over A, I could just flip them both upside down. They'll still be equal. So that would be A over 1 equals 1 over sine 30, which is pretty much exactly what I wrote there. If we did sine 30 on a calculator, we're going to see that sine 30 is 0.5. So it's actually a very nice number. So I'll replace that here in the equation. So A equals 1 over 0.5. And if you do that on a calculator or in your head, multiply the top and bottom by 2, we get A equals 2. So that gives us the second side length. So if that side is 1, that side's going to be 2. Now for the third side, we're going to go back to our old friend Pythagorean theorem. It's a right triangle. We know 2 of the sides. So that's ideal for Pythagorean theorem. Okay, so remember Pythagorean theorem is c squared equals a squared plus b squared. probably shouldn't use that since I'm already calling this A, and I'm going to be calling this B for now. But if I was using this, it's always the hypotenuse side squared. So that's going to be 2 squared is equal to this side squared, which is 1 squared, plus the third side squared. So that's B squared. So I can quickly figure that that's 4, that's 1. I could get B squared is equal to 4 minus 1, or B squared equals 3. And then I take the square root and I get B equals the square root of 3. So that's my third side. So I've accomplished what looked like something very difficult. I was able to complete using the sine ratio and Pythagorean theorem. Okay, so the next part says, we're still working with this triangle. With these side lengths, find the following trig ratios using SOHCAHTOA. Keep as fractions. So no rounding, just one number over another. So let's remind ourselves, SOHCAHTOA. Okay, so sine 30, I go back to my triangle here. That tells me the reference angle is here. So sine is opposite over hypotenuse. So using 30 as our reference angle, opposite would be 1 and hypotenuse would be 2. So opposite over hypotenuse is 1 over 2. So sine 30 is 1 over 2. And that is backed up by what we did on the calculator a few minutes ago. When we did sine 30 on the calculator, we got 0.5, which is 1/2. So that works. Cosine 30, so we're still using 30 as our reference angle, but cosine is adjacent over hypotenuse. So this time adjacent is root 3 over hypotenuse, which is 2. So cosine 30 is root 3 over 2. And if you try to do that on a calculator, you get your screen filled with digits. This is the exact value of cosine 30. If you do it on a calculator, you're going to get it like a rounded decimal version. So we call this the exact value compared to the rounded or non-exact value. If we keep going using 30, so you can see so far we've used 2 of the 3 ratios with our reference angle of 30. Tan 30 would be opposite over adjacent. So opposite is 1, adjacent is root 3. So tan 30 is 1 over root 3. And now we're going to switch gears. We're going to now look at the 60-degree angle as our reference angle. So remember, when that happens, the opposite and adjacent sides change. So now this is the opposite, this is the adjacent, compared to 30, where it was the other way around. So sine 60, so remember sine is opposite over hypotenuse. So this time opposite is root 3, and hypotenuse is 2, so root 3 over 2. And then cosine 60, remember cosine is adjacent over hypotenuse. Adjacent is 1 and hypotenuse is 2, so that's 1/2. And then finally tan 60, opposite, so this time opposite over adjacent is root 3 over 1, or just root 3. So we've actually got our 6 exact values for these 3 trig ratios for 30 degrees and 60 degrees. So you can see that comes directly from this triangle, 30, 60, 90 triangle. One thing to point out here is we have a couple of duplicated values. So if you notice, sine 30 is the same as cos 60. And also cos 30 is the same as sine 60. And that's really no coincidence. The fact that the two angles 30 and 60 add up to 90 is the reason why that happens. Okay, hopefully we'll talk more about that later. But it's good to see where the similarities are sometimes between the ratios. All right, so we're going to move to our second triangle. So this triangle is called the 45, 45, 90 triangle. So no no real confusion here. You have a 90-degree angle and then two 45-degree angles. You notice because these two angles are the same, this is actually an isosceles triangle. So normally we're looking at the side lengths being the same, makes the two angles in the corners the same, but it's true the other way around too. So if I made this side equal to 1, well, that side's also going to be the same. So we've already got two of our three sides laid out, so all we have to do is figure out what that third side is. And again, we can use our old friend Pythagorean theorem, since it's a right triangle and we know two of the three sides. So if I called this side C, I know that that's the hypotenuse, so it would be C squared equals 1 squared plus 1 squared. C squared equals, well, that's 1 plus 1 is 2. And then I take the square root, I get C equals the square root of 2. Okay, so let's do the same thing. This time we've only got one angle, 45, because it's actually replicated. So we don't have as many calculations to do here. So still using SOHCAHTOA, so I guess I could use any of these two as reference angles. It makes no difference. So I'll just point to this one. So sine 45 is going to be opposite over hypotenuse. Opposite is 1, hypotenuse is 2. So sine 45 is 1 over root 2. And cos is going to be adjacent over hypotenuse. Well, adjacent is also 1 over the hypotenuse of root 2. So again, you see duplicated values here. And then tan 45 is opposite over adjacent. Well, this time opposite, adjacent are both 1. So 1 over 1 is 1. So this is an interesting angle because the sine and the cos values are the same, and the tan value is equal to 1. Okay, so let's carry on. Okay, so we're going to look at this from a slightly different perspective. We're still working with sine. Sine of an angle equal to a value, or cosine or tan. But we're going to go back and revisit and look at our special triangles again to help us out here. So sine x equals root 3 over 2. So remember, the variable x there represents an angle. So we're actually kind of working backwards and saying 2. So if you remember on the previous page, we wrote down, well, you can see it here, sine of 60 is root 3 over 2, and it's the only sine value that has a result of root 3 over 2. So if I just wrote sine 60 equals root 3 over 2, well, you can compare these two equations. And one thing in math is if two equations, if you got two equations and in this case the right sides of both equations are the same, well, that means the left sides of the equation are also the same, so that means sine x equals sine 60, so therefore x must be equal to 60 degrees. Okay, so it's kind of working backwards. We're going to find a much more efficient way of doing this with the unit circle, but for now, we're just looking at the idea of working backwards. If we know the ratio, trig ratio, can we get the angle that gives us that ratio? Okay, try the same thing here with cosine ratio equal to 1 over root 2, and we just did that one, if you remember. We're looking for cosine. We saw that cosine 45 equals 1 over root 2. So if I repeat that here, zoom in a bit. So cosine 45 equals 1 over root 2. So by the same argument that we used before, we have 1 over root 2 on the right side, cosine of an angle. Therefore, the angles must be the same. Therefore, x equals 45 degrees. Let's try one with tan. Tan x equals 1 over root 3. If we go back to our first triangle, we saw tan of 30 is 1 over root 3. So if I wrote that out, tan 30 equals 1 over root 3. This tells us that, well, x must be equal to 30. So an angle of 30 degrees gives us a tan ratio of 1 over root 3. Okay, let's try these where we're going to get exact values. So unlike some of the calculations we've used with the trig ratios where we have to round our answer because the calculator is filled with digits, we're actually going to get exact answers, meaning they're not rounded. So if I look at this picture here, I've got a 60-degree angle here in the corner, so that means that's 30, of course. So since they gave us this angle 60, I'm going to make that the reference angle. I don't have to, but I'm going to in this case. And then based on that, well, this side's the hypotenuse, this side is the opposite, and this side's adjacent, but I don't need to put it because I don't know the value for that side. If I use the sine ratio here, so the sine of 60, now the reason why I'm using sine is because I know sine has opposite hypotenuse, and those are the only two sides that I actually know. So it wouldn't make sense using cosine or tan here because it uses the adjacent side and I don't know what it is. So sine 60, and I'm using 60 because that's the angle given, sine 60 equals opposite over hypotenuse, which is, let me put the letters opposite over hypotenuse, which is equal to x over 12. Okay, so that's straight from that picture. But from previous work, I'm not going to flip to it, but we also know that we know the value of sine 60 is actually equal to root 3 over 2. So I can kind of compare these two. We've got sine 60 equals x over 12, and also sine 60 is root 3 over 2. So therefore, x over 12 is equal to root 3 over 2. Okay, so what I can do, I can solve for x because that's what our goal is, find that side length. I can solve for x, multiply both sides by 12. So that's going to get rid of that 12. It's going to be 12 root 3 over 2, and I can divide out a 2 on both sides, so x is equal to 6 over 1, which is 6 root 3. So that is our exact value of that side length. Okay. Previously we would have gotten a long decimal value that we'd have to round at some point. This is exactly the right answer. Okay, let's try it with another question here. Again, this time we've got right triangle, 30-degree angle in this corner. So this will be our 30, 60, 90 triangle. We've got this side as labeled as x. That's what we want to find. We know one of the other two sides over here is 8. So again, this will be my reference angle. And I'm thinking what ratio uses these two sides? Well, if that's my reference angle, this is my opposite side, this is my adjacent side. So what trig ratio uses O and A? That's tan. So I'll write my statement as tan 30 equals O opposite over adjacent, and opposite over adjacent would be 8 over x. Okay, but again, also on the previous page we also learned that tan 30 is equal to 1 over root 3. So again, we've got two things that are both equal to tan 30, 8 over x, 1 over root 3. So I can make my equation from that. 8 over x equals 1 over root 3. Now I'm going to apply that trick that I talked about previously, but I didn't actually use it. I really want to get x. When x is on the bottom, it's a bit of a problem because I can't just multiply both sides by 8. It's going to make it worse. So I'm actually going to flip it upside down, both fractions. So x over 8 equals root 3 over 1, which is really just root 3. And therefore, if I multiply at this point both sides by x, I get x equals 8 times root 3. So again, that's the exact value, no rounding. And you notice both of these answers have a root 3 in, which was a number that was on one of my special triangles. Okay. So we did a little bit of work with those special triangles that allowed us to find unknown sides based on those special triangles. We're going to end the lesson with a couple of different things that will be needed for once we work with the unit circle. The first one is something called angles in standard position. So this will be brand new for grade 11 and on into grade 12 as well, of course. Talking about angles, and when you think of angles in grade 10 or before, you're thinking of this kind of V-shaped thing that just kind of floats in free space, and I could turn this in different orientation. It would still be the same angle, of course. These side lengths would be the same. It's just kind of floating in space. Well, we have a new concept now. Instead of free space, we're basically going to clamp down this angle on the XY coordinate axis. So there's our old friend at the XY grid. So when we put this angle on the coordinate axis, what we do is where the two sides meet, that's going to always be at the origin. The angle at the bottom will be along the x-axis, and we call that the initial arm. And then the other arm will be basically coming off the origin at that same angle as it was when it was floating in free space. So, so the second arm, the one that we're kind of going from the x-axis from, or the initial arm from, is called the terminal arm. So initial arm, terminal arm, you can see that this is the beginning, this is the end. We always start measuring our angle from the initial arm to the terminal arm, but one important concept is we always go counterclockwise. So the angle is always measured going in this direction. It's not going in this direction. We can go in the other direction, but it would be a negative angle. Okay. So this is an important concept for the next lesson. When we actually construct our unit circle, we will be working with angles that are on the XY grid. Starting at the origin and working our way out all around. Okay, so if we want to apply this concept, well, now all of a sudden, instead of just being confined to triangles, where the angles are usually, well, most of the time 90 degrees or less, sometimes 180 or less, now we can have just about any angle drawn on the coordinate axis. Okay, so what do I mean by that? Well, let's draw some of these angles. See, I've got 1, 2, 3, 4, 5, 6, 7. So let's do, maybe I'll do 5 and 3. There, so that's enough. Okay, so I'm going to go just work my way through these angles. So if I'm drawing a 90-degree angle in standard position, that's the terminology we use. So that means we start our angle here at the positive x-axis, and we go 90 degrees counterclockwise. So that means we're going to end up here. So this angle here is 90 degrees. Okay, I won't put my arrows in, but they should be there. So there's my initial arm, my terminal arm. Angle between is 90 degrees. So if we bump up to 180 degrees, again, initial arm on the positive x-axis, and where I draw my terminal arm will be measured as I rotate around the origin 180 degrees. So that's 90. Another 90 would be here. So basically it's a flat line. And I'm measuring my 180 degrees like that. Okay, if you keep going, the next one was 270. So again, that would be another 90 degrees counterclockwise. So still starting here at the initial arm, positive x-axis, rotate around 270 degrees this time. So that takes us down here. So there's our terminal arm. Notice that we go counterclockwise every time. I'm not measuring that angle. If we go clockwise, what happens is we can go clockwise, but it's a negative measurement. So that would actually be negative 90 degrees. Okay, and we'll be talking about how they are related in example 5. So this is 270 degrees measured from the initial arm to the terminal arm. And now we've got not necessarily multiples of 90 anymore. 70 degrees would be our next one. So again, initial arm is the positive x-axis, and we rotate 70 degrees. So we don't get to the 90 degrees. It's going to be a little 20 degrees short of that. So there's the terminal arm, and the angle inside here is 70 degrees. Okay. Next one is 150. So you can kind of know where it is. We know all the way here would be 180 to there is 90, so it's somewhere in here. That would be called quadrant number 2. So initial arms always here. Terminal arm would be 90 plus another 60, so it's about right here. There's the terminal arm. There's my angle in standard position, and that's 150 degrees. Oh, I think I missed one, didn't I? 1, 2, 5, 6, 7. No, I've drawn one too many of these. Okay. All right, so that's 150 degrees, angle in standard position, meaning initial arm is the positive x-axis. Rotate in a counterclockwise position to get my terminal arm, and that's an angle in standard position for 150 degrees. 210 would be our next one. So remember, 180 takes us to there. So 210 would be another 30 degrees here. So initial arm here, terminal arm here, angle in standard position there. That's 210 degrees. And then finally 300 degrees. Well, we know 270 is down here. So we need another 30 degrees past there, which would take us to about here in the terminal arm. But angle in standard position, meaning we start at the initial arm, the positive x-axis, rotate counterclockwise 300 degrees to get to the terminal arm. Okay, so these concepts we talked about: initial arm, terminal arm, angle in standard position. The fact how you measure the angle is always counterclockwise. If you go clockwise, it would be the negative value. So for example, if I measured from here to here, this angle would be negative 60 degrees. Notice if you go around the circle completely once and get back to where you started, that's 360 degrees. We all know that's 360 means go around in a circle. So one rotation would be 360. And you can keep going from there. If you extended, you could actually go to 400 or 500. Okay, and that's what this next section is. And we will be talking about, we call these coterminal angles. So coterminal, remember we just talked about terminal arm. Coterminal angles means it has the same terminal arm, but you may go about getting there in a different way. For example, if I went, instead of going clockwise, instead of going counterclockwise, I went clockwise this way, that would be, say for example, negative 300 degrees, which would be the same as 60 degrees. Okay, so what we're going to do here, I can come up with an infinite number of coterminal angles just by adding and subtracting multiples of 360 degrees. I can keep going around in the positive or negative direction, certain number of rotations. Each rotation is worth 360 degrees, either negative 360 going clockwise or positive 360 going counterclockwise. So what we're being asked to do here is take a look at each of these angles, and you can see, some of them are negative, some of them are pretty big, some of them are within the 360. But what we want to do is convert each of these into a coterminal angle between 0 and 360. And I'm not going to draw the sketches here, but I'm going to come up with some other angles that would be coterminal angles. Okay, so for example, negative 40 degrees. Okay, that's obviously not between 0 and 360. If I wanted to do that, I would just add 360 to that. Negative 40 plus 360 gives me 320. So that's within the 0 to 360. So that's kind of the goal. But I could keep going and add another 360. Actually, let me do the math here. Okay, so to get the next angle, it's always the original angle plus or minus multiples of 360. So if I just add 360, I'm going to get 320 degrees. So those two angles, negative 40 degrees and 320 degrees, we call these coterminal angles because they would share the same terminal arm if we were sketching these. It's just about how many times you go around the circle or which direction do you go when you go around. Okay. The next one, negative 193 degrees. So again, that's obviously not between 0 and 360. So looks like we'd be okay if we just add one revolution or one multiple of 360. If we do that, we get 167 degrees. So in this case, negative 193 degrees and positive 167 degrees are coterminal angles. They would share the same terminal arm if we sketch these. 375 degrees, well, that's a little bit over the 360. So instead of adding multiple of 360, we're going to subtract. So it looks like all they need to do is subtract one 360. So instead of adding 360, I'm going to subtract 360. And I'm going to get 15 degrees. So 15 degrees and 375 degrees are coterminal. Okay, let's keep going. 400 degrees. So in this case, we're going to subtract 360. And we'll get 40 degrees. So 40 degrees and 400 degrees are coterminal angles. Try 500 degrees. So start with the 500. Again, we're going to subtract. It looks like 360 would be enough to bring it between 0 and 360. So that actually leaves us with 140, and that's good. So 140 degrees and 500 degrees, coterminal angles. 140 degrees, well, that's already within the range, so I don't have to do anything with that. Now, I could find, for each of these, I could find multiple coterminal angles. Just add another 360 or subtract 360 as many times as I want. I can come up with an infinite number of coterminal angles. The goal of this exercise was just to come up with a coterminal angle that's between 0 and 360, so that's what we're doing. Okay, 820, this seems like probably the most difficult one to do. So I'm obviously going to have to subtract at least 360, and it looks like 360, one multiple of 360 would not be enough. So I'm actually going to subtract 2 times 360. So that's 720. Subtract that from 820, I get 100 degrees. And that shows us that 820 degrees and 100 degrees are coterminal angles. So these are just concepts that are important for the rest of the unit, just to get some terminology down straight. So we've got the angles in standard position, we've got initial arm, terminal arm, and now we've got our coterminal angles and how they're related to each other, and how you can come up with a coterminal angle that's within 0 to 360 range. That's going to be important. Okay, got some homework questions for you to work on and practice this. And then the next lesson we do, critical lesson, we're going to learn about the unit circle, and that will help us in our future lessons in trig in terms of finding all sorts of sine, cosine, and tan ratios. Okay, all right. Hope that made sense to you, and we'll see you on the next lesson. Take care.